Okay, good morning, everyone. It's a great pleasure to be here. And what I'm going to tell you today is work that we've been doing to essentially implement in calculations the CWL theory on nanoparticles with the view to using quantum states of these trapped nanoparticles to probe the effect of gravity on the quantum mechanics of large systems. So this is work done with Kai Ellis, graduate student in my group at Berkeley, and in collaboration also with Jordan Wilson-Jarrow, who's now a Burke postdoctoral fellow at Caltech. So for those of you, this first slide is for people who are not so familiar with physics and the idea of quantum superpositions, and it's a nice visual representation from Fred Wolf showing how, just in very simple terms, intuitively, we can understand what a superposition is and also how measurement plays a role in probing superpositions. So you see at the back, at the top here is a wire mesh cube, and depending how you look at that, namely whether you're looking and focusing on the furthermost corner, you might then be looking, you feel inside the cube, or look at this, see this kind of projection, or if you're looking at the front corner here, you will be projecting onto this particular representation, which is an outward-facing cube. And so these two different orientations come from our interaction with this somewhat ambiguous representation of one single object. And that's, in the layman's terms, the idea of a superposition, quantum superposition. And on this slide, I put together some examples, all of them examples where superpositions of, in three cases, superpositions of mass have been observed, and the last case is superposition of flux. So starting on the top left here, this is the work of Wineland, which won the Nobel Prize in 2012. This is a superposition, emotional superposition of a trapped ion, which starts in a particular internal state and essentially a ground state of a harmonic oscillator here, and is then, by a sequence of laser pulses, transformed into this state here, where half of the superposition has amplitude in a different internal state, located in a position over here, and the other half of the superposition has the lower internal state, and the wave packet is located about 80 nanometers to the right. And this is a superposition of one atom with mass 10 to the minus 26 kilograms. So this is basically the classic type of superposition for microscopic atomic scale objects that physics takes nowadays for granted. So on the right here is work from Markus Arndt's group in Vienna, which takes this notion and tries to scale it up to very large molecules. So this is a molecule with, I think, 4 porphyrin rings attached on long chains. It's about 2,000 atoms, so it has mass now about 10 to the 3 larger, but still small on macroscopic scales. And they have set up a molecular diffraction experiment with this, in which the effective separation between the peaks corresponding to these peaks in the wave packets here, the separation is now of the order of 500 nanometers. So this is a big step forward, but it's still very far from the macroscopic regime. So on the left, at the bottom here, we have experiments from Andrew Cleland's group in Chicago with a mechanical resonator, where we now do have something more approaching a macroscopic number of atoms. This is a mechanical resonator made of aluminum, aluminum nitride, and aluminum layers, shown here on the right. And it has 10 to the 13 atoms now. So the mass is orders of magnitude larger, it's 10 to the minus 13 kilograms. And they managed to put this oscillator, basically a mechanical oscillator or resonator, into a state, so-called dilatation state, where this central lip here is basically expanding and contracting. And they put it into a superposition of 2 vibrational modes, and the effective separation, or the extent of the motion in that dilatation mode is now very, very small, 2 times 10 to the minus 16 nanometers. So there's a kind of playoff here. You can go to a larger number of atoms, but then the difference between the two states in terms of real space is now very small. And that's because this is a vibrational mode of the resonator, and therefore the wave function of the center of mass is essentially confined within approximately the same region. So you get a very small overall displacement. Something very similar happens with flux superpositions in superconductors, and as Philip mentioned this yesterday, I thought I'd say a few words about this, because this example demonstrates the subtlety in defining or thinking about what the effective size of a superposition is. So this flux superposition occurs when you have a superconducting ring and separated by one or more Josephson junctions. And you can set this the system up so that you have a superposition of current flowing in the two different directions, clockwise and counterclockwise. This was a long time goal of people in superconducting physics, and it was achieved in about 2000 by 3 different groups. I've shown here only the numbers from the group that had the largest effective size. So this is from Jonathan Friedman's group at SUNY at the time. That has 10 to the 13 electrons involved in the currents, actually involved in the difference between the persistent currents going left and right. And the size of the ring was about 500 micrometers. But we looked at this very carefully in terms of the measure I'll show you on the next slide. If you look at how many particles are actually doing something different in this motion, in this superposition mode, it's actually only 10 to the 4, approximately, of order 10 to the 4 electrons in different modes. And it's really the same idea as in here, where if you consider the vibrational motion of the center of mass, there's really only a very small displacement. But if you consider the total number of atoms, you would think you get a much larger number. So just to summarize here on this side here, we developed at that time a measurement-based measure, which is basically an operational measure, and you have to then choose what you're going to measure as the size, to determine the size of the superposition. And so we wrote this down as a minimum number of particles that have to be measured to distinguish the 2 branches. And you can show that, theoretically that this is indeed equivalent to the size of this superposition. And so then this boiled down for this instance to ask how many electrons are different momentum modes in the 2 branches. And so this is written down here for just counting the number of electrons, but you get a very similar result if you measure the Cooper pairs, which is just a harder calculation. So when we did this, we found this somewhat surprising result, that whereas this difference in persistent current gave orders of gave an estimate of 10 to the 10 for the difference in magnetic moment, which was proposed by Leggett as a measure of the size of the superposition, and also we have 10 to the 13 electrons involved in these currents, that when you actually look at how many electrons are doing something different, you have a number more like 10 to the 4. And that's partly due in this case to the Fermi statistics, and partly also due to the fact that we're looking at motion of electrons. The ones which contribute are those which are very close to the Fermi surface. And there's a very small difference there. But so that's just a cautionary tale that it's important to think about how we actually measure these superpositions, if we can even generate them, and what it means. So now let me come to the main part of the talk, which is the focus on gravity. This is a beautiful picture from Dirk Baumeister, which indicates schematically how one particle here would be put into a superposition state, and then schematically the idea is that the gravitational fields associated with these particles will somehow interfere in a complex way. So there's various questions that this raises. We're focusing at Berkeley and Caltech on the question, in the calculations I'll present, we're focusing on the question, how does gravity affect a mass superposition? And we're going to consider the gravitational interaction between the 2 parts of a superposition, and we're not going to worry about the effects of the Earth's field of gravity. So you imagine it being done basically in free space. So when we're going to use the CWL theory, and we're going to actually try to make a calculation with the CWL theory. So this is the only slide that I'll give, which will I'll say a few words about, comment on the meaning of CWL and what's actually in it. On the left-hand side, so the CWL theory, as Philip said yesterday, the basic starting point are paths in space-time. And so think about the path integral representation of quantum mechanics as the starting point. And in the left diagram here, we have illustrated the difference between standard quantum mechanics and quantum field theory path integral representations, where one has two paths between two endpoints, and each one may have interactions along the path, but there are no interactions between paths. These paths are independently summed, and there are no interactions between them, so as in the Feynman path integral. On the right-hand side, we see the second one here on the right shows the same paths, but now with also interactions between these individual paths, which are mediated by gravity. And this has, as Philip laid out the theory, this starts with full general relativity, and Philip has very nice arguments showing that it's basically the principle of equivalence says that in a gravitational case you should have these interactions between the paths, but you wouldn't have such interactions between paths if you had a straight Coulomb interaction. So on the right is how we basically where we can take off to do calculations. Basically, the fundamental quantity we're interested in is the propagator between states alpha and beta. But now, when we actually do calculations, we usually like to think about states in a representation. So here, in a position representation. And so here, we're contrasting the regular propagator from, in the Feynman sense, which would go from, say, x1 to x2. That's broken down into a sum of independent paths between x1 and x2. And then you integrate over x1 and x2 to get the propagator from state to state. Now in CWL, we make replicas of each of these propagators. So it's shown as these solid lines here, connecting the states alpha and beta. And then each of these replicas has interactions between the paths inside it. And also, most importantly, there are interactions between the paths from different replicas. So there's interactions between the paths in this replica and the paths in this replica here, and then between all possible pairs of replicas. So then our path integral becomes a product over n, capital N path integral. And we can do this to different orders. So we start at 1 and we go up to some finite number n. And then the theory says we take a root alpha n of this, and then take the limit that then goes to infinity. So this is a rather complicated procedure, which makes it difficult to do the calculations. Jordan has shown that the alpha n can be conveniently, basically the leading term is basically 1 over n here. So this is the quantity ultimately that we want to compute, where now the action in this n-dimensional or n-replica path integral, the action now contains the action due to whatever external potentials we have on individual paths, but also then all the gravitational interactions between individual replicas. So now I'm going to go straight to the explicit calculations that we're doing. We're considering the effects of CWL interactions between replicas for a finite extended body. So we have n atoms in the extended body. And so on the left here, we've shown schematically 2 replicas for part of the lattice of an extended body. So we're considering a crystalline body, so we have a well-defined interatomic spacing A and different sites Rj, Rk. And the replicas are labeled R and R prime. So we're also, everything we're doing in these calculations is in the limit of weak gravitational field, non-relativistic system, and Newtonian gravity. So we're going to I'm going to show you some exact calculations, but we're going to start with perturbative calculations, and the perturbation is always in the sense of summing all the Newtonian interactions, not perturbative in the sense of curvature effects, including curvature effects. So if we consider these two replicas, then Jordan and Philip showed that the effective CWL action has this form here, where these sums now are over the interactions between atoms on one replica, and J, and atoms on another replica, J prime. So these terms divide into diagonal terms, like this interaction right here, and then off-diagonal terms, so diagonal terms between the same lattice site on different replicas, and off-diagonal terms between different lattice sites on different replicas. So, sorry, let me go back. So the off-diagonal terms would be this site here on the blue interacting with, say, this site here on the red. So what they showed was that this divides into two. The off-diagonal terms give a smooth potential, which has an effective quadratic form, and the diagonal terms, however, give rise to these spikes. So that's shown here, and here's the form of this spike, which has an error function, and then one can expand this to see that this also has, in the weak coupling, this has a quadratic-like form. So this basically tells us that there's an effective quadratic potential coming from the diagonal terms, which dominates in this inter-replica potential. And what we're interested in are cases where shown here, where the center of mass, so recall this is the center of mass coordinate, so we're interested in cases where we can localize a particle, a nanoparticle, inside this spike potential here. And that's when we expect to get the greatest CWL contribution. So we're specifically making calculations for the kinds of nanoparticles that Marcus Aspelmeyer's lab has been working with, which are made of silica, have diameters 150 nanometers, and so they have basically delocalization of the order of 10 picometers. And the width of the spike potential is of the same order of magnitude, a little bit larger. And this plot just shows the very rapid fall off between the atomic wave functions with separation, so that you can, if you are localized inside this spike potential, then the diagonal terms truly are dominant. The off-diagonal terms would have contributions way out here. Okay, so the first thing we might consider is that if we took an initial Gaussian state, so took a nanoparticle sphere trapped in a harmonic oscillator potential, and now that's the external potential, and we would consider how does the position distribution of that state as a function of time, what is the effect of CWL on that? Well, it's quite easy to show that in that case, if you're looking at a position measurement, there is no effect of CWL, because the first two assumptions here will allow us to separate the final state into the replica center of mass and the relative coordinates, which is what we're doing all the time in the calculations. And then the third step says that because we're doing a position measurement, then the final relative coordinates are all 0. And since then, the initial coordinates are integrated over, so there's no dependence then of the final state on the relative coordinates at all, and the CWL action depends only on those relative coordinates, and if there's no dependence of the final state on that, then there's no dependence of the final measurement of position on any CWL effects. So if we have very simple observables like position measurement, we wouldn't expect to see anything for a harmonic system. So now we consider instead a displaced oscillator, and instead of doing the position measurement, we'll consider a state-to-state propagator. And we're going to use a perturbation theory to evaluate this. This is just the first calculation. And I'll show you there are some issues with the perturbation theory afterwards, but just to get an idea of what could possibly happen in the weak gravity limit, we'll take a perturbative approach. So we have these three frequencies essentially in the problem. We have the harmonic oscillator frequency, the external potential. We have the spike potential frequency, which comes from the diagonal contribution to the CWL interaction. And that gives us an effective harmonic frequency, which goes in the action for our propagator. So here's how the perturbation theory works. This is outlined in detail in Jordan and Phillips' PRD paper. So basically, the idea is that one expands these propagators in order of the Planck length squared, which basically says expanding in orders of g. And then truncating, if you truncate at the very first order, then you simplify this entire very complicated tower of n replica propagators to just 2 replica interactions like this. And so then in this approximation, we have to consider, we have to evaluate this transition element here, which has a denominator of the bare transition element, and has in here the action from the 2 different paths without CWL, and here is a CWL perturbation. To avoid the possible zeros in this denominator, which will certainly appear for a harmonic system, we choose the initial and final states such that this 0th order term is 1. What that means is that we're projecting the state onto its 0th order time evolved state. So this is a very artificial calculation, but very well defined. So our initial state, we have 2 replicas of the displaced harmonic oscillator ground state. Our final state is chosen such that at a given time t, this 0th order propagator is 1. So this is a time evolved, image of this state here. And then we carry out the perturbative CWL calculation, and we arrive at a modified propagator, which has the usual phase term here, which you would expect. And is in Feynman's textbook, Feynman and Hibbs textbook. You can find that there. And then we have this correction factor here, which is extremely small. If you put parameter numbers in for the nanospheres, you get this turns out to be something of the order of 10 to the minus 9, so that then in terms of non-unitarity corrections, they would be order 10 to the minus 18, so vanishingly small. But this is interesting because it's the first calculation that shows for a specific system there is some non-unitary CWL correction to quantum state dynamics. So now we want to go on and consider a non-Gaussian initial state, in particular a momentum superposition state here. But before we do that, we want to improve the theory somewhat, because we've assumed here that the initial state is actually a product state, which isn't a CWL state. There should actually be CWL correlations in the initial state to be consistent. And secondly, there are some issues with doing perturbation theory. Let me summarize those issues here. So we have this expansion parameter, the square of the Planck length. But in CWL, we have to scale the gravitational constant to compensate for the fact that we have n replicas. And so that scaling is shown here. We have our gravitational interaction, and then we scale it by 1 over n. We scale g by 1 over n, so that when we have n replicas representing the system, we still get gm over r. So the CWL, that means that the CWL interaction will have this factor of 1 over n here. And when we sum over different replicas, and this sum is now over the j's and k's are on different replicas, so then we'll have n squared terms from this sum, and then we'll get a CWL potential, which scales as n times g. And then since n has to be taken to infinity in the CWL theory to get the full propagator, then we cannot, this suggests that we cannot do a perturbation expansion in Gn. So we should be analyzing the quantum dynamics non-perturbatively. Again, where I mean non-perturbatively is fully summing all the Newtonian contributions. So we're going to do that. Before I do that, though, let me take a bit of an experimental digression and think about how would we, so we're going to do it for these momentum superpositions. I'll show you, okay, these little guys down here. I'll show you a bigger picture of that in a moment. How would we think about generating these? So I've got 2 slides here showing you sort of going from the simplest Gedanken type experiment to something which is actually happening these days in Marcus's lab. So on the left is a very simple Gedanken experiment that Jordan and Yan-Bei Chen are thinking about at Caltech. So first of all, if you think about a single photon coming into a beam splitter, splitting into 2 parts, 2 amplitudes, 2 components of a superposition, and then impacting on a nanocrystal here, a nanoparticle, and then interacting and imparting a momentum kick to the nanoparticle. then they are passed through another beam splitter, and if you have single photons, you can show that this will enable you to do photon counting at each of these two detectors, and in one case you'll get the positive superposition shown here, and in another case you'll get the same superposition with the negative sign here. So these are states that are entangled between the, these are states where you have psi 0, you've disentangled the state from the photon. Now, of course, the single photon interaction with a nanoparticle is incredibly weak. So you can think about amplifying this using a laser, and then you'd have an amplified interaction here, and then the analysis here would be somewhat more complicated, but the same principle would hold. So another option is to use Bragg scattering, and I went to talk to my colleague Holger Müller in the physics department who does this, and one could think about putting an NV center in a diamond, a nanocrystal, and the NV center has a very strong optical transitions, and you could then basically do, so this is a typical diagram that they show for Bragg scattering, where you have counter-propagating laser beams with wave vectors k1 and k2 corresponding to the Raman transition, and that gives you a net momentum transfer of h bar times the difference, k1 minus k2. And this can be extended fairly easily to 5 minutes. Good. We're good, because I've only got 4 more slides. But you can do much better than this, better than Raman. So with Raman transitions, you can go up to about h bar k, 8 h bar k. But with, if you're using only single photon interactions, you can actually do much better. And that was first developed by Mark Kasovich, who's here. And his former student Hogan has now developed really cool experiments showing momentum transfer up to about 140 h bar k. This is still, though, not enough to give a significant kick to a nanocrystal. There you need several thousand optical photons. So another approach, which Marcus will probably talk about on Thursday, says, well, let's replace, and I understand there's lots of experimental reasons why you actually might want to avoid having the photon nanoparticle interaction. Instead, they use a pulsed optical potential, and in particular, if you take a cubic optical potential, shown here in this second pulse here, then you can generate essentially something that looks like a momentum superposition, except instead of momentum here, we have x cubed, and so this is basically a superposition of momentum states, and that's shown here on the right. So this is a theoretical paper. I understand this might well be the way to go in near-term experiments. So with that, let me show you how the calculation works and what we would predict for this. So this is the idea. We have that's one of these methods has created a momentum superposition of a particle moving in an external harmonic oscillator. And we want to, in this case, now we have the non-Gaussian initial state, so we can think about computing the final position, position distribution. So we basically need this propagator where I've just summarized the effect of CWL on the dynamics of some effective Hamiltonian. And we have the momentum operator kick generates a superposition. And now we are taking, for the ground state here, the CWL correlated ground state. I won't show you the details of that. Jordan has worked that out. But we're doing everything consistent. And we're doing this also non-perturbatively. So we're basically doing this with n replicas. And then we have to take the 2 over n limit to get the probability. And then we'll take the limit of this, then goes to infinity. So this will give us a probability distribution which is not normalized, which is because of the non-unitary nature of this evolution here. And so we have to renormalize this, and that's the goal of the calculation. So this is the schematic how it works. If we have a momentum superposition, we have n replicas here, and then we will perturb this, we will time evolve this non-perturbatively in this sense here, and then we will evaluate this quantity, which will then finally allow us, if we can take these, the root and this limit, will finally give us this probability distribution. So we're not there yet. What I am showing you here is basically the intermediate calculation. We have got the time-evolved state, psi here, which has this n dependence here, and we now have to think about how to take the nth root of this, and then, so first of all, we take the square to get the probability distribution, then take the nth root of it and take the limit. And so that's more work to do, and we're working here to see if we can get some analytic estimate for that to give us this distribution. So that's work in progress. So now let me just then summarize. So basically, I started from the starting point is that the momentum superposition states of trapped nanoparticles show promise for analyzing the effects of gravity on dynamics of non-classical quantum states. And also they are under development experimentally, so that's great for a connection. Jordan may talk today, on Thursday when he talks, he may mention what you can gain by going to somewhat larger particles, which isn't so far off from Marcus's system. If you go to the micrometer diameters, they have larger CWL effects because the larger the mass of the particle, the narrower the extent of the center of mass wave function, so the more you can localize the center of mass wave function in the spike potential. So on the theoretical side, going forward, we will want to be doing more detailed analysis of the generation and control of these superposition states, and also, very importantly, to consider the influence of environmental decoherence on these superpositions. So I haven't said anything about any kind of source of decoherence, just like I also neglected the effect of external gravitational fields. I think the key takeaway from this talk, though, is that it's possible to make non-perturbative, in the sense of full summation of Newtonian contributions, it's possible to make such non-perturbative CWL calculations for trapped massive particles of relevance to current experiments. And so with that, thank you very much, and I'll answer any questions.
Time for maybe one or two questions, but we're kind of running behind. Okay. Let me give you the mic.
So these are very simple questions, but I was a little bit confused between the talk that Philip gave and the talk you gave just now, because Philip was saying that there are no Hilbert spaces, but you clearly had, that there are no Hilbert spaces, but it seems that you had a clear bracket here, Hilbert spaces. Yes. Furthermore, that at one stage you had a Hamiltonian.
I should have changed that. That's really evolution under the action. That was left over from an earlier. Yeah.
So there is no Hamiltonian, is that right?
No, there is. There's a Hamiltonian, the external potential, and then there's also the CWL interaction, which gives each path an effective additional potential.
Right.
So if you want, so you could, yeah, it's not a physical Hamiltonian in a sense. Yeah.
So it's not a Hamiltonian in the Hilbert space?
So I don't think there's a contradiction with what Philip was saying, because in the end, so the basic quantity is a propagator, and Philip agrees that the propagator has to propagate from one state to another, well-defined quantum states. The point is, though, that those quantum states are themselves, one point is, those quantum states themselves are CWL correlated, which is a question of state preparation.
Right. No,
but then, if you were about to evaluate that propagator, we convert to, we like to represent quantum states in position representation. So we actually then express them in position representation, and then we have the propagators between individual position eigenstates. So the propagator is then in position representation. So we use all the language of conventional quantum mechanics, and that's okay to do, but you do find at the end that you have a correction that's non-unitary.
Yeah, so if you have a correction that is non-unitary, that means that the effective Hamiltonian would not be self-adjoint. And my question was, can we just look at the effective Hamiltonian and see it is not self-adjoint? And you know what the...
Yeah, so I shouldn't have written a Hamiltonian there. I should have just written S, actually. Yeah. Yeah, we're not giving any interpretation to we're not interpreting that as a Hamiltonian. That was really just a shorthand for we're doing dynamics under the action, including the CWL